very exciting result on the entanglement in ground states. Itai, yeah.
Okay. Thanks. Thank you, Anurag. Thank you for the organization and inviting me. And this is a work with Arad from the Technion and with Raoul Jain from the CQT in Singapore. And I'm going to talk about area laws for maximally mixed ground states in arbitrarily degenerate systems with good AGSP. So I hope in the end of the talk, it will be understandable what these kind of words all mean. Okay, so let's start. So the subject of the talk is area laws, and to define area laws, we consider a many-body quantum system. Usually we think about it as some spins sitting on some sort of a lattice, d-dimensional lattice, like in here. And what the area law, when we say that the system has an area law, it says something about the entanglement structure in this many-body system. So what does it mean precisely? It means that if we do some sort of a partition of the system into some L and the rest of the system, L complement, and we look at the entanglement entropy between this part and the rest of the system, then it behaves, it scales like the surface of this area rather than the volume of this area. Usually, if we take a random state, the entanglement entropy will scale like the volume, but in specific states that satisfy the area law, we have much, much less entanglement, and it scales just like an area. Okay, and this is kind of a peculiar behavior, because usually in physics, entropy is an extensive quantity that scales with the volume and not with the surface. So this is something rather special. And the reason that we're interested in this thing is that it turns out that area law do happen in natural systems. And in particular, we have the so-called area law conjecture that conjectures that if we look at ground states of local Hamiltonians, and these ground states are gapped, so there is some finite distance between the lowest energy, which is the ground energy, and the next excited energy, then we expect to see this behavior in the ground state itself. Okay, so the ground state of gapped system, in other words, should contain much less entanglement than arbitrary quantum states. Okay, if there is any question, just stop and ask me. Okay, so what do we know about this conjecture? So this conjecture has been proven for few cases. It's still an open problem to prove it in its full generality. It was first proven by Hastings for 1D systems in 2007 for gapped system, and then it was proved using different method. It was the bound on the entanglement was improved in 2013. And for 2D systems, there are also some results, but usually these results assume some extra conditions above the existence of a gap. So we have, for example, if we have particle-like excitation, or if we have a low density of low energy states, etc. And also if the system is frustration-free and it has a local gap, so every patch of the system has a spectral gap by itself, then we can also prove this for 2D system. Okay, so these were previous results, and all these results hold for the case where the ground state is unique. Now, what I wanted to discuss in this talk is the case where the ground state is not unique, and in fact that it is highly degenerate. So there are many, many different ground states. So what do we know about these cases? So when we have some degeneracy in the ground state, and the dimension of the ground space is now R, then we can actually use many of these methods and prove area law for a basis of states inside the ground space. Okay, but every time the bound will deteriorate a little bit, because what we are doing, we are kind of proving an area law for one guy, and then we are looking at Hamiltonian, which is the original Hamiltonian plus some projection on that guy, particular guy that panelizes it, and this kind of thing makes the bound on the entropy worse and worse. Okay, so what we can easily show is that in such case, in the cases where we can prove it for the unique case, we can also prove it for some degeneracy, but then the bound worsen, and we get this factor of log R, where R is the overall degeneracy of the ground space. Okay, and the point is that this bound makes this result kind of trivial when the degeneracy is really high. Yeah.
So is it a worst case over what's in the ground space, or is it the least entangled thing in the ground space?
No, it's the worst case.
The worst case. Okay.
There will always be some guy in the ground state that is as good as the unique case.
Okay.
But the worst case would be this thing. And the worst case is really is actually, I mean, you can easily see that it happens. For example, you can look at this non-interacting system or 1D system where we have Q-treats. Okay, and the Hamiltonian is just projecting out the two state. Okay, so the ground space here is just the 2 to the n options of all possible states with 0 and 1. So it is a gapped system, and it is a local Hamiltonian, and the degeneracy is 2 to the n. And of course, we can have any state of 2 to the n on n qubits here. So we can have as much entanglement as we want. Okay, so that tells us that that it is hopeless to improve this result. Okay, so but what can we still say about the case where the ground state is highly degenerate? So there's.
I want to just say that there's a basis which has low entanglement.
Sorry.
Don't we want to say that maybe there's a orthonormal basis with low entanglement?
Yeah, there is, but I mean, it will progressively get. Okay, you say that maybe there is a specific basis where each one of them is. I cannot rule that out. I mean, it might be true, but I don't think it's true. But,
in this case, it's true, obviously.
In this case, it's true. Yeah, you can take a. Okay, that's a good point. I don't know. Okay.
In fact, would you expect that if all gapped Hamiltonians are like adiabatically connected to that one, then what you may say it should be true? Circuit that repairs rotates that basis.
Okay, that's a possibility. Okay.
Already.
Yeah. Okay. Nevertheless, I do want to concentrate about one particular state inside the ground space, which is the maximally mixed state inside that. So we are looking now at the mixed state, which is the equal combination of all the states in the ground space. And I would like to ask whether this particular state satisfies an area law. Okay. So so when we talk about mixed state, then we can no longer talk about the usual entanglement entropy. Instead, what we should talk about is the mutual information, which reduces to the entanglement entropy in the case of pure states. But this is actually what the quantity that is that we should try to bound. And then our setup is this: we have some local Hamiltonian, we have some bipartition of the system, we have a degenerate ground space, and we are looking now at the maximally mixed state inside this space. And the question that I would like to ask is whether there is an area law for the mutual information for this particular state. In other words, does the mutual information between L and L complement scales just like the boundary? Okay, so let me try to motivate why this might be true and why this might be interesting. So from physics point of view, I think that the maximally mixed state is the most natural or physical state in the ground space. And the reason is that this is just the limit of zero temperature as of the Gibbs state. Okay, so we look at the Gibbs state of the system. This is the state of the system when it is at a certain temperature in a thermal equilibrium, and we can take the temperature to zero, and we get that the state of the system will be just this maximally mixed state. In addition, we know that for every finite temperature, if we are on a local Hamiltonian, then the Gibbs state satisfies an area law for the mutual information. So therefore, it would be nice if we can somehow show that it also holds in the limit where the temperature goes to zero. And finally, it trivially holds also in the commuting case. Okay, in the commuting case, well, the maximally mixed state, I can just, usually I can, I mean, in all cases, not just in the commuting case, I can just write it as a projector to the ground space and normalize such that the trace will be 1. But in the commuting case, I can break down this overall projector into products of projector. So there will be one projector projecting on the ground space inside our region, one projector outside, and there will be some boundary term projector. And because the boundary term projector, well, it lives only on the boundary, it will not create too much entanglement, and the amount of entanglement that it would create will just scale like the boundary, so it will automatically satisfy an area. So the main result that I would like to present here is that if there exists a good AGSP, a D delta AGSP with this condition, then the mutual information is of a region is upper bounded by this quantity. So I will explain what a good AGSP and what D delta and all these parameters mean. But what this result specifically said, it doesn't prove an area law per se. It just says that if we can construct a certain operator that satisfies this condition, then we have some bound on the mutual information. And in particular, if we can construct this operator such that this log D scales like the boundary, then it will give us automatically an area law. Now we can use previously, I mean, known constructions for such operators for 1D and 2D, and that will automatically prove the area law for the cases that we knew how to prove in the unique ground state case. Okay, so the outline for now would be, I will first give some outline about what AGSP is and about this framework for proving area laws. And then I will introduce some tools from quantum information that I would need, which is the min-max smooth entropies. And then I would be able to give an, well, almost formal statement of the main result. And then I will try to give some, to sketch some ideas about how this proof comes about. Okay, so let's start with this AGSP. So AGSP stands for approximate ground space projector. This is given a system, a many-body system with some Hamiltonian, then the AGSP is just a many-body operator that tries to approximate the projector to the ground space. Okay, so it is this operator K, and it is characterized by two numbers, D and delta. What do we require from this operator? So first thing, it should preserve the ground state. Okay, so for every state inside the ground space, it should be invariant on this operator, just like a projector. But then it will not kill completely everything that is outside the ground space. Okay, but instead of killing it, it will shrink it by some parameter, and this parameter is the delta. So in some sense, the delta tells us how good this approximation is. Okay, when delta is equal to 0, this is the exact projector to the ground space. But in addition, we have this other parameter D, and what D does is to control how much entanglement we create as we apply this operator to some product state. So how much entanglement do we create across this particular bipartition? So specifically what it tells us that the K can be written as a superposition of D product states. That means that if I apply K on a product state, I will get a state with the Schmidt rank, which is at most D. Okay, it will be written down as a superposition of at most these product states. Okay, so that kind of controls how much entanglement I have. And yeah,
would delta scale with the size of the projector? Like, is this like a projector in space where you're sort of saying approximately it's the ground state over here in this region?
No, the ground space is the global ground space.
I see.
But the AGSP, the operator is constructed for a specific bipartition. So for a given bipartition, I might have different values, these parameters, D and delta.
Okay, great, thanks.
Now, we say that a K is a good AGSP if it satisfies this condition, if D squared times delta is smaller than 1/2. Intuitively, it means that this guy does not create too much entanglement. I mean, there is this trade-off here between how much entanglement you create and how accurate you are. And if the product of these two things is smaller than something, then that means, okay, I can approach the ground space quickly without creating too much entanglement. And that's kind of an indication for that I might have an area law. Okay. Now, why do we care about about AGSPs? The reason why we care about them is that we have this so-called overlap bootstrapping lemma. And what this lemma tells us is that suppose we have an AGSP, which is a good AGSP, and we have some ground state of a unique Hamiltonian, then if we can construct such K with d delta, with the product smaller than 1/2, then it promises to us that there exists a product state between L and the complement with a large overlap with the ground space, with the ground state. Okay, that tells us that in some sense this ground state does not contain too much entanglement. Okay, and that would be the first step in proving an area law for this particular bipartition. And the intuition why is what I said before. I mean, if K has two things, I mean, it has this D that creates entanglement, and it has this delta that takes us the speed in which we converge to the ground space. And if delta is stronger than D, then in some sense we will converge faster to the ground state. We will not be creating too much entanglement on the way, and therefore the ground space will not have too much entanglement. This is the way where, using this framework, it is possible to prove an area law for 1D system. That's what was done here, and also for 2D system, which are frustration-free and two-dimensional with local gap. Now, I want to stress something important, that this lemma, as I will show you now, is a trivial lemma. It's just like one page. Okay, the entire energy and the entire effort that comes into proving area law is in the constructions of the AGSP themselves. Okay, and and what is kind of funny in this work is that the entire energy is actually comes into play into generalizing this lemma, this bootstrapping lemma, for the case of the mixed ground space. Okay, so that's kind of the strange thing. Okay, so let me just give you a short, show you why it is such a simple thing to prove. I mean, this bootstrapping lemma in the case of a unique ground state. So we start with some ground state of H, and we assume that we have this good AGSP, and we want to show that there must exist some sort of a product state with a large overlap with the ground space. And the way we do it is that we start with the best product state that we have, the guy that has the largest overlap, and we expand it in terms of its projection on the ground space and its projection to the complement space. Now what we do, and of course the coefficient before the ground space will be exactly this overlap, and this is exactly the thing that we want to lower bound. Okay. Then the next step is simply to apply K. We apply K on this product state. We get some unnormalized state phi. And because we know that K does not create too much entanglement, I mean, it will create a state that has a Schmidt rank of at most D, then we can expand it in the Schmidt decomposition like that. Okay, so this is the Schmidt decomposition of phi. And on the other hand, we know we can just, because we can use this expansion of the product state, we know that K doesn't do anything to the ground space, to the ground state, so it leaves it as it is. And on the other hand, it does act non-trivially on the thing that is perpendicular to the ground state, and it will actually shrink it. So now what we can do is we can now take take an inner product of phi with the ground space. And so on one hand, we get just mu, the overlap. And on the other hand, we get this this bunch of overlaps with the Schmidt vectors. And the important thing now is to note that since we assumed that the biggest overlap is mu, then this sum here can be bounded by this expression. And we can just now take off mu and get this this equality that the sum of the Schmidt vectors is bigger than 1. And using the simple Cauchy-Schwarz, then we get this expression here. And what we have here is none other than the norm of phi squared, because it's the sum of the Schmidt coefficients squared. And all we have to do now is just insert our estimate for the norm of phi, which would be just mu squared and delta. Delta is because of this guy is shrinking the ground space, the part of the perpendicular to the ground space by amount of delta. So we get this thing, and we play around with the coefficients here, and voila, we get that mu squared is bigger than 1/2D. So it's just like half a page or 1 page proof, and it's completely simple. So the entire thing, the entire problem here, using this framework, the entire challenge is to come up with such an operator K. Okay. So let's see how we can do it for the maximally mixed state. So for the maximally mixed state, what I would need some tools from information theory. So so I would actually need what is called the Imax and the smooth Imax quantities that kind of generalize the mutual information. So let's start with the definition of mutual information. I can define the mutual information by first considering the relative entropy. So the usual relative entropy of two states is given by this formula, and the mutual information is just, and I can look at the relative entropy as some sort of a distance between these two states, between rho and sigma. And then the mutual information is just the the distance between rho A and its marginals, okay, between of some partition. And I can also write it down as the minimal distance actually between rho A and AB and some product rho A times rho B. Okay, that will be actually, you can show that these things give you exactly the same thing. So now I can define what we call the maximum relative entropy. So given two states, rho and sigma, such as the support of rho is inside the support of sigma, I can define the maximum relative entropy by this expression. So what do we want here? Well, we look at all the possible t's such that t times sigma will be a greater operator than rho. And we take the minimum of that, and that will be and we take the log of that, and that will be the minimal relative entropy. And that we should view it as some sort of a distance between rho and sigma. And the intuition is that if indeed rho is smaller than 1 plus epsilon times sigma, then it tells us that actually these two states are very close to each other, up to 2 epsilon. Okay, so once we have this notion of distance or relative entropy, we can define the Imax, the mutual information with respect to this to this relative entropy, and it will be, and just like this definition here, it will be just the minimal distance or the minimal distance that we have from a product state. Okay. And one last thing is that while this quantity is easy to analyze from a combinatorial point of view, it is highly sensitive, and it is just like the Schmidt rank. Okay, it's quantity that can fluctuate enormously, even though the underlying state does not change too much. Okay, so instead of that, what we will also consider will be a smooth version of this function. So the Imax, the smooth Imax with some epsilon, will be just defined as Imax over a ball inside in a distance of epsilon from rho. Okay, so and there is another fact that is not too hard to prove, and the fact is that the usual mutual information is bounded by the smooth Imax of epsilon plus some error of epsilon plus L. What this fact tells us is that if we can somehow bound this quantity, then we can automatically get a bound for the usual mutual information, and this is what we actually want to bound, right? We want to bound the mutual information between these two regions. Okay, so now I can give you the main results. So we have the first theorem. The first theorem says that if we have a local Hamiltonian, and with respect to some bipartition, we have a good AGSP that satisfies this, then the Imax is bounded by this expression here. So notice that as epsilon goes smaller and smaller, I mean, the bound becomes worse and worse. But as we show, as we saw here, I mean, it doesn't. I mean, we can we can use a finite epsilon to get a bound on the actual Newton information, and therefore here also, if I take epsilon to be 1 over L, this gives me a bound on the actual Newton information. Okay, so that's kind of strong enough to prove an area law. And using known construction for AGSPs, if I just plug this construction inside this formula, I get this type of area laws for 1D and for 2D. So for 1D, I get an area law with some logarithmic corrections, and the same thing for 2D. I mean, there will always be some sort of a correction. So it's not, we cannot prove strict area law in this case. Okay. Another theory, another result that we can prove, but I will not prove in this thing, is that we can also prove that there exists a tensor network, an efficient tensor network description for the maximally mixed state. Okay, and in 1D as what is called an MPO, a matrix product operator, with bond dimension that scales like n over epsilon, and it will give us a trace distance between this operator and the actual maximally mixed state of about epsilon. Okay, so it's a strong characterization of this mixed state. Okay, so let me give you try to sketch some idea of the proof, and again, I think the proof itself, I don't know how much it is interesting, but I think what is interesting is that how much work you should put inside in order to prove it, whereas in the unique case, I mean, it's just like 1 page. Okay, so what is the approach? So let's recall that the Imax is just the minimum over all the product states and over this T, okay, that we can, such that rho will be smaller than this T times this product state. So just like in the bootstrapping lemma, what we can do now is we kind of start with the best guy we have, okay? So we take the best product state and the smallest possible T such that rho max is smaller than these 2 guys. And our task is to upper bound T. Okay, that will give us the bound on the Imax. Okay, so one thing we can do is we can take this expression here, and apply an AGSP on it from both sides. Okay, now this is an operator. It's no longer a pure state, so I have to apply the AGSP on both sides. So doing that and using the fact that the AGSP does nothing to the ground state, so on one hand, I get that this expression is equal exactly to rho max. On the other hand, let's apply it on this part of the equation. We still have this inequality because we are using some positive super operator. And what I can do now, applying k on this thing, I get something which is positive, but is no longer normalized. Okay, so I can rewrite it as the norm, the trace of that times some normalized quantum state. Okay, and what I can do now is this is a rather easy observation, that because we know now that the Schmidt rank of tau is upper bounded by d squared, because remember each one of these k has at most d guys, then it's not too hard to see that there must exist two guys, tau L and tau LC, such that tau itself is smaller than d squared times their product state. Okay, that's kind of a distance from this from this tau, and plugging this into this expression here, we get that rho max is smaller than t times this expression times this product state. But now recall that we started with the optimal guy. Okay. And this is just another product state that we use to bound. So we can actually use this to compare what we have here to this. So we can conclude that necessarily what we have here must be bigger than this optimal bound, because this is the smallest bound. So we get this inequality. The T is smaller than what we have here. And unfortunately, this T drops out, and we get this inequality. So the fact that T drops out is not so good to us, but let's go on and see what it gives us. So we got this inequality, And the next thing we can do is we can now expand the product state with part that is on the ground space and part that is perpendicular to the ground space and plug it back into this trace. And using the fact that the AGSP does nothing to the ground space, we can see that, and the parts that are perpendicular to it are shrinked by the AGSP. We can conclude that this trace must satisfy this inequality. And then plugging it back here and doing the same thing that we've done before, we get some immediate inequality about this quantity here. But what is this quantity? This is the overlap of this product state with the ground space projector. Okay, so we got that this overlap is lower bounded by some number, which is kind of what we had in the pure case or in the unique case. But unfortunately, this is not strong enough for us, because what it gave us some sort of an overlap, but we wanted an upper bound on T. Okay, and let me try to convince you why it is not good enough. It is the main reason why we can't really do anything with that is that, okay, we understand that there is some product state that has a large overlap with the maximally mixed state, okay, because it has a large overlap with the ground state projector. But that doesn't mean that it necessarily implies an area law to the ground state. And the reason why is that, okay, we can start with this guy and we can apply the AGSP, but it doesn't, because the ground space ground state is not unique, it doesn't mean that we will end up in the maximally mixed state. Okay, so that cannot help us to actually prove a lower bound on the entanglement and entropy of the maximally mixed state. Okay, because we don't know where this thing will lead us to. So instead of a lower bound on this overlap, what we actually need is an upper bound on T. That's what we needed in the first place. And this is where we actually think about flat states. So this is a small part. What is a flat state? A flat state is a state that I can write it down as in the spectral decomposition as a convex sum of states with the same weight. Okay, that would be a flat state. And why would flat states help us? Well, flat states are a specific case that if, for some God-given reason, these two guys, sigma L and sigma L complement, were flat, then it's a very easy exercise to show that the overlap is directly related to this T. So having a lower bound on the overlap will automatically give us an upper bound on the T. Okay, but unfortunately, nobody tells us, nobody guarantees to us that these states are flat, so we cannot use it as it is. But this is more or less the motivation of using other tools. So what we end up with is instead of having a simple bootstrapping argument, as we shall see, we will have a sequence of state, and we will somehow perform a bootstrap on each one of these states, and we will have some sort of control of how flat the states are in each one of these steps. Okay, so the second main ingredient in the proof is the so-called brother extension, and the brother extension, it was pioneered by Arad et al. No?
20 years older than that work.
Ah, really? Okay, sorry. In that paper, we actually stated. Okay.
Oh, really?
Yeah. Okay. So it was used also in the quantum case 20 years, or in the classical case? Ah, okay. So, but in the quantum case, you were the first, right?
Yeah.
Okay. So the idea of the brother extension is that if we get a state that is not flat, so if we expand it in the spectral decomposition, it has different weights. What we can do, we can introduce another auxiliary space, and we can define some sort of an extension of this state into the overall space, such that in the overall space it is flat. And if we trace out the auxiliary space, we go back to getting this state. And so, for example, if we have this state here, which doesn't have equal weights, we can introduce a new register B, and then we can come up with a new state which is flat here. So the idea is now to use this machinery and we just use it as a mathematical tool to control how flat these sigma L and sigma LC are. Okay, there isn't really any physical meaning behind this extension. So, I can't really explain the details of this proof. I mean, I will not, there's not much of a point, but as I was saying, there is some sort of a sequence of states here, and and using the brother extension, we can somehow control how flat these things are and end up with a bound that relates the overlap to the actual max entropy.
So maybe going back a little bit.
Yeah.
So you said that if sigma L and sigma R were already flat,
Yeah.
then it is all okay.
Yeah.
But yeah, this part.
Yeah.
But is there a way to understand that as, is there a more intuitive understanding of that? As in, is it like when you apply the AGSP, if it's flat and you apply the AGSP, then you actually get close to the maximum mixed state and not to some other state in the case?
Could be. That's a good intuition.
Okay.
Yeah, I think it would be true actually, right? I mean, because well, depends on the AGSP, right? I mean, yeah, the AGSP can distort it a little bit, but
the ground space component should still stay.
sorry.
The ground space component. Yeah, right. Okay.
I mean, I will be brutally honest with you. I don't have good intuition for this group. That's why I'm desperately looking for something simpler than that. Okay, so I will spare you the analysis, and this is where the proof becomes extremely technical, and that's why it kind of spans like more than 10 pages instead of 1 page in the unique case. But let me just go jump to the summary. So we proved what we actually did was to prove a bootstrapping lemma for an area law for the maximum mixed ground space, which is independent of the underlying degeneracy of the space. Okay, so so this shows that if we have a good AGSP, then we have an area law in the mutual information for the maximally mixed state, and then using existing AGSP constructions, we can prove an area law for the maximum mixed state in 1D system and in locally gapped 2D systems, frustration-free. And our proof also guarantees that there is an efficient tensor network representation for this state. And unfortunately, I mean, it uses really involved tools from quantum information theory, like the smooth min-max entropies and the brother extension, and which make the proof rather involved. And some open questions about it. So the first question, which is, I think, for me, is most important, is there a simpler proof for that? Is there a simple combinatorial proof, just like in the unique ground state case? Okay, I mean, I think it has to be. I mean, I don't. Another interesting thing to do is whether this work can be generalized not just for the ground space, but also to the case where we have like a highly degenerate and low energy spectrum. I mean, can we say something about the projection or the maximum mixed state in the lower part of the spectrum? And another interest related to that, I would say, is another question: can we use this thing? This kind of thing kind of proves that if we have a good AGSP, and good AGSP we know can exist if we have a local gap, then we have an area law for the 0 temperature. But we also know that we have an area law for any finite temperature. Can these two results be somehow combined and prove that we have an area law for the Gibbs state in all temperatures, all across? And finally, I mean, another place where we have high degeneracy, in some sense mixed state, is if we look at, for example, 2D systems of frustration-free 2D system, and we just look at the one slice of that system. So here, if we just look at this Hamiltonian, we would have a lot of degeneracy. So the question is whether this type, and what we know is that we have some very strong locality now constraint about the ground, about the maximum mixed ground state here, which is exactly up to a scaling the projector on this thing. So can we somehow use these locality constraints on this projector here to maybe come up with a different proof of the 2D area law? So that's another, I think, an interesting direction. Okay, thank you.
Thanks a lot for a great talk. Some questions?
So for the second point that you mentioned, in this case, why do you expect the maximum mixed state in the low density spectrum to do the right thing rather than the Gibbs state itself?
I mean, I would say that first of all, if I'm not mistaken, if you already have the situation where you have a lot of an exponential number of state low energy state, and then you have some sort of a gap above it, then maybe you can already use an AGSP that we have to prove the existence of a good AGSP, and then without changing this proof too much, I mean, you can already directly prove an area law, because I don't think we actually use the fact it's the exact ground state.
Yes.
So maybe it would be easier in this scenario.
Yes.
And what's known about Gibbs state area laws?
Well, we know that it exists for any any finite temperature, and do we know anything else? I don't know.
Yeah, that's the only thing I know.
Okay.
So that would be constant.
Yeah. And actually, the proof is quite simple in that case. I mean, it's
But it doesn't extend to anything
not that I'm aware of.
And we know that at high enough temperatures, Gibbs states are separable. I don't know if that helps with anything.
Yeah, but I mean, but for even any low but constant temperature, there is it's easy to prove an area law. You don't.
But this suggesting could there be a stronger version of that?
Sorry?
This suggesting could there be a stronger version of that?
Yes, maybe.
It's sort of an unrelated question related to your last point, I guess. What breaks in higher dimensions? Like why?
We don't know how to create a good AGSP in higher dimensions.
I see.
I mean, that's right. All the effort in proving these area laws, in this framework at least, boils down into constructing good AGSP, and you used to polynomials of the Hamiltonian and tools from approximation theory, etc. And it's really hard to go beyond 1D. We only have one good example, I think, in 2D under some extra assumptions. So this is a challenging point.
And the information theoretic tools that you use, they're not available for the higher dimensional cases?
Well, I just used them. I don't know, maybe they might be useful in this case, but I didn't touch here on the construction of the AGSP. I'm kind of assuming that I have a good AGSP, and then, okay, can I use it to prove an area law? So that was the place where I needed to use all these fancy quantum information tools.
Good sequence of hand cases.
So in 1D, the area law, or at least the techniques for the area law, allow us to actually get an efficient algorithm to prepare it, right? Not as an MPO.
Yeah, right.
Is there anything similar you could say for the degenerate case, given that now you get a area law for 1D?
I don't know. That's a good question.
I assume there's probably a lot of missing.
I would say it should be possible. I mean, to kind of use dynamical programming to find this MPO, but I don't have a.
So Sandy, do you have a half handle as a half question?
Yeah, do you expect the area law to hold in the higher dimension?
Yeah.
Yeah, so from the physical point of view, I mean, physicists know when it's gonna hold or not.
Yeah, I mean, I wouldn't put all my money on that, but I would expect.
Like often in the many-body case, we hear about like behavior of the gap as we scale the system size and so on, right?
Right.
Talk about gap really means like it vanishes polynomially or something like that. For you, you have these approximate projectors. Do you understand anything about how they behave as I scale the system size?
Yeah, well, usually what you have is you assume you know the gap.
Yeah.
And the and the gap itself, or your estimate for the gap, goes into the construction of the
Right.
AGSP. So it goes there explicitly into it, and then you can see it. And
Okay,
and
so-
for if you use it for example, bounding the entanglement entropy, you would usually see that it is bounded by 1 over the gap.
Okay,
So-
so are you assuming like the number of degeneracy scales with like I have an extensive
Yeah.
surcharge?
Yeah, but the gap remains the same.
Is there anything you can say about having like, somewhere slightly less integrable, right? If I had a slightly sub-extensive number of conserved charges?
In a way, you mean that thing? It's a statement about the degeneracy of the ground space.
Yeah, sorry. Okay, yeah, maybe that wasn't obvious. Right. I'm imagining that the degeneracy of the ground state is telling me something about the number of symmetries I have in the Hamiltonian.
Right.
And so, like, roughly speaking, I have in mind that, like, oh, the system is integrable, right, when there's an extensive number of conserved quantities. And so I would expect that that means that the degeneracy of the ground state is extensive.
Yeah.
But, like, if I, like, perturb away from that and start going towards chaos, is there anything you can say?
Well, all the constructions that we have for AGSP, they don't care about the degeneracy too much. I mean, actually, if I'm not mistaken, right? I mean, they're agonistic to that. I mean, so you can have whatever degeneracy you want, and you take the same formula for the AGSP, which usually uses some component of the Hamiltonian to create this operator.
Okay, so it's not important that, like, the rank of the AGSP is, like, the size of the ground state sector or something like that.
No, it does not depend on that.
That's interesting. Thank you.
So how robust is this proof when the degeneracy is only approximate? Say they're all in like exponentially small window, or like
I don't know. Actually, that's one of
So-
the open questions I want to. Intuitively, I would say that you can make it robust if you have small.
Okay. Okay, if no more questions, thanks for the
We'll take
break and we'll be back with a non-quantum specific talk.
Yeah.